We are live. Good evening, everyone, and welcome back to the LLM Bootcamp Zero to Hero in LLMs. Today, we'll continue with the module 3 of module 4. And yesterday, we had attention model mechanism, and continuation to that, we have transformers implementation. And today, we have Aritra Roy, who is a machine learning engineer at PyImage Search. He is also Google developer expert in ML, and apart from that, he is a Hugging Face Fellows. And he'll be explaining how you can get started with transformers and what are the architecture blocks which are within the transformers layer. And then we'll move on with the code walkthrough. And without further ado, let's start with the session. Over to you, Aritra.
Thanks, Tarun, for having me. And I guess people are already familiar with attention because my good colleague Ritik yesterday took a session on attention. And I'm going to do a continuation of what he said, and we'll try to build that up into the concept of transformers. So, Tarun, could you please take the slides up? That would help. Right. So, welcome everybody. I am Aritra Gosthipaty. I am a machine learning engineer at PyImage Search. I also am a GDE in ML. So, without blabbering much about me, what we are going to cover is transformers, and this is going to be a little offbeat as to how people usually cover transformers. I'm trying to figure out or maybe experiment a new way I can teach transformers, and that is uh, due to the fact that it's new. I would like people to comment as to whether they like this approach and also interact with me in the session more than make it feel like I am just blabbering into the void. So comments would be much appreciated. Right. So going like starting absolutely with what we are trying to do with this LLM bootcamp is we are trying to model text. And how do we model text? There are a bunch of methods to model text. One is supervised learning. Then comes self-supervision, transfer-based, prompt-based, and whatnot. So what is supervised learning? So supervised learning, you have this a corpus of text, and by a corpus of text is what I mean is a collection of text, and you have labels which are mapped to these texts. So like here, we have COVID cases are increasing fast, and that those labels are negative, neutral, and positive. So the model is telling us that this sentence, COVID cases are increasing fast, has a negative connotation to it, right? And this is how or this is how supervised learning kind of comes into place, where you have input and you also have a ground truth along with it. Now, a little caveat about supervised learning is that you don't have good labels. You don't have too much of text with labels in it. So it's very difficult for people to train these models because the data is very sparse. You can't train a very big model because there is not very good data in the wild which is properly labeled. So in comes self supervision, in which you don't have labels per se, but you model the task in such a way that you kind of derive labels in the task itself. So as you can see, self-supervised has language modeling and masked language modeling. So what do we mean by language modeling is you give a bunch of text and you stop and you ask your model to predict the next word and also complete the sentence for that matter. So what you can see here, my name is Thomas and my main is the text that you give to the model, and the model uh, prompts out or gives out or generates the next word. So goal is to make sure that I am not just a guy who everything you see here is the generated text. And think about it properly. So we don't need to have a text and a label to train this model. Rather, we just have to have a bunch of text, and we can stop at any time and just ask the model to predict the next word, and that's the entire task. So the problem that supervised learning had as to a lot of text and mapping ground truth kind of mitigates. So this is how we come to self supervision, wherein I am the data and I am providing supervision myself. So self supervision. Another task is masked language modeling, wherein we mask certain bits of our entire text corpus and we ask the model to generate what this mask was. So fill in the blanks. So here, as you can see, the goal of life is mask, and there are a bunch of labels, or there are a bunch of words that can come in, and the model predicts which word has the highest probability or to fill in the mask. So in that way, we again have a bunch of text. We just mask pieces out, and those masks are something which we already have in the data. They are not labels, but we are molding the task in such a way that these are behaving like labels. So in the comments, if you all understand what the con of supervised learning is and how self-supervised learning comes into play, that would make me feel very good. So just a plus, or maybe yes, I understand would do. So I'll keep a check on the comments. If there are no comments, I'll get back to this slide maybe later. And moving on, there are these two parts that I don't want to cover in much depth. This may be covered in the later modules of this bootcamp. So transfer learning and prompt based learning. Transfer learning is once you have a pre-trained model, you transfer that knowledge into specific tasks. That is, you fine tune your pre-trained model, and that is how okay, I see and I understand. Thanks for that. So transfer learning is where you transfer your knowledge base into specific tasks. You have a pre-trained model and you fine tune that pre-trained model onto a specific task. So say for example, you have a very big pre-trained model and you want to fine tune it on, say, sentiment classification or maybe question answering. So these are specific tasks that you can transfer your knowledge to. So transfer learning. Prompt based learning is very interesting, wherein you have a pre-trained model which is very generic, and you give it prompts to not train. That is, you don't have to update your parameters of the model, but the model will give you zero shot good answers to that specific task. So say for example, you have a big model and you prompt the model with a statement and ask it what is the sentiment of this of this sentence, and it's going to give you an answer. So that is how prompt based learning works. It kind of molds its entire knowledge base into what you are trying to prompt out of it, and this has been an active research scope. So that's good. What is our main motive today? Our main motive is to understand language modeling itself. So just a recap of what language modeling is. You have a bunch of text, you stop at some place, and you want to predict the next, that is the current word or token or whatever, given a set of prefixes. So I am a good, this is a prefix, boy, that comes right after the entire prefix, is what we are trying to figure out. So that is language modeling. And turns out language modeling is really interesting and also gives birth to a lot of architectures. The entire task is something which people have been doing a lot, and it's also proven to be a good strategy for pre-training. So language modeling, to dumb down the entire thing, we have a prefix of words. So x1, x2 to xn minus 1 can be thought of as words. So here students opened there is a order of words, and given students opened there, what is the probability that books comes into play? That is the entire task that we are trying to model. So if you think about it, students opened, if you give just students opened, what is the probability that there comes in, right? So given a prefix, what is the word that comes in? That is language modeling. And to predict that probability and make that probability score go high is what we want. A little hand wavy things of where we are at. So think about students opened there, and you put all of this in a function, and we'll call this prefix for the rest of the session. Prefix is something which comes pre to what I want to predict. So prefix, and I want to predict a word or a token, which is, say, books. So students opened there is a set of words that is a prefix that goes into a function f. We'll come to what f is a little later. And f now gives a probability distribution of all the vocabulary that I have. So think about the problem statement properly. So you have a bunch of words in your vocabulary, and a vocabulary is nothing but the unique words that you can predict. So there, the vocabulary might be books, laptops, students, opened, house, dog, cats, whatnot. Once you give all of this prefix into this function, the function is bound to give you a probability distribution over the entire vocabulary, so that you can sample out the most like the word that has the biggest probability which is mapped to it. Does that make sense? uh, Even I'll be checking on the comments, so don't worry if I'm going too fast, too slow. Please comment it out. I'll adjust accordingly.
There is one
Okay.
question like,
Mhm.
does mask and label in same context? This was asked while you were explaining self-supervised learning.
Okay. Mask and label in same context, yes. So once you mask something out, you can think of that mask as the label that you are trying to generate, and that is required, to have a loss. So once you mask something, the model generates a word, and that word needs to correspond to the actual word that was there, which was masked. So that is kind of the label that we want, and due to the fact that this label is not something like a sentiment, something that has been annotated exclusively, hence the term self supervision. So, whatever we mask, we already have the label, and the label is used for the loss. I think that makes sense. And moving on. So, F. Now comes the function which is of our interest. What is this F? Is this function the RNNs, LSTMs, GRUs, or transformers that we are going to cover in our bootcamp? Think about it again. F can be broken down into two components, where the first component is computing a representation, and the second component is a softmax. And the softmax function has been covered thoroughly in the previous session of LLM bootcamp by Ritik. And what he said is, if you have a vocabulary of a lot of words, and if you have a prediction over those vocabularies, you can apply this softmax function. It gives you a probability distribution over this entire genre of words, or the collection of words. So softmax is really important for you to get the probability distribution. But what comes a layer behind softmax is computing a good representation. So once you have all these prefixes, I'll go back to the slides where I can show you these prefixes. Once you have these prefixes, you need some function to formulate a representation of the entire prefix, right? So if you think about it, students opened their books or laptops might depend on what students were doing, whether the students were inside of a classroom, were inside of their individual homes, whatever they were doing. So it's very context dependent. So we need to have a lot of communication between these prefixes to form a good representation. And this representation then goes on to predict what I'm trying to achieve. So a food for thought: if you don't have good representations, you might get a probability of another word. That does not mean that the word is wrong. That just means that the representation was not good enough that could model the entire context of the sentence. So therefore the function might give students open their laptops rather than student open their books, because it did not know that students were in library. Does that make sense? So the context is really important, and a good representation is important too. Thinking about that, computation of a representation is something that RNNs, LSTMs, GRUs, and transformers take care of. And today we are going to talk about transformers. And before that, before we jump into transformers and whatnot, I'm going to do the experiment that I was referring to. I'm going to start from scratch, connect a collab notebook. I have a bunch of code written, so don't worry about me typing furiously and having a bunch of errors. I'll just go in cell by cell and also try to formulate why transformers is the way it is. And maybe then I can open up to a discussion or a dialogue about what we need to do later and why transformers work off the bat. So to do that, the first things first, import torch. And people who know me, they know what blasphemy I have done right now. But it's the easiest way to maybe go through the entire collab notebook, because Torch provides me with some leeways which TensorFlow or JAX did not. So hard luck. And we do this. So what I mean by B, T, and C is that B is the batch size, T is the time steps, and C is the channel dimension. So if you go back to the ordinance lecture that was taken by Tarun, or maybe even the attention lecture that was taken by Ritvik, you will all understand that a token, maybe a word, maybe a character, a token can be represented into a dense vector. And this is important to understand, because if we do not represent these tokens into vectors, we will not be able to model properly in a space where we can do vector arithmetic. It's as simple as that. So what I'm trying to suggest here is, if you have similar words, they are going to point to a specific direction as two similar vectors would. And if they are orthogonal to each other, that means that the meaning, or the two tokens, are very different from each other. So if you think about words as vectors in a space, it's going to be very intuitive to understand the entire scene of what we are trying to achieve. So think about words to be vectors pointing in different directions, and similar semantic words, or similar or words that have similar meaning, point to the same direction, have equal lengths or whatnot. And words with different meanings, they are far apart, they are either in the opposite direction, pointing against each other, and that sort of things. So what we are trying to emulate here is that I have four a batch size of 4. That means I have 4 sentences, and each sentence contains 8 tokens, and each token has 2 dimensions each. So I just want to model each token in 2 dimensions. So I think I am understood. It's very hand wavy. I apologize for that, but it is very interesting to understand how the field of natural language processing has intuitively taken a lot of understandings of vector processing. So 482, 4 is the number of sentences, 8 is each sentence contains 8 tokens, and each token or each word has 2 dimensions for it to be represented in this space, in this vector space. So 482, that's how we come to that magic shape. Now let me ask you a question, and this is open to everybody who is watching this right now. What I wanted to do is language modeling, and with for language modeling, what I also mentioned is that to predict a word, I need to see the prefix. So students opened their book is something which I want to predict, but all the prefixes needs to communicate to me so that I, the model, can predict book or predict laptop, right? So I need to make all these tokens communicate to each other. The best way to communicate to each other is a simple summation, right? You just aggregate all the representations of the previous or the prefixes and aggregate them together, and that is how you will feed that aggregated vector to me. I, the model, will predict out books. Is there a better way of doing it? What I wanted to say is I can sum it up, but a problem with summation is the scale. How can I take that down? What should be a little intuitive way to maybe scale down the sum? I just want to sum it up. So even Tarun, who is in the back looking for, like, hosting this entire event, you are open to answer that as well. I'll wait 2 minutes. If there is no answer, I'll move forward.
There is some response like fine probability.
Okay, anything else? How would I make all of these prefixes or the words communicate to each other? I said summation is a good first way to go, but I want the sums are very tricky, because if I have 3 words, that means the sum is nearly about roughly in the scale. But if I have 100 words, if I have 500 words, the sum is going to shoot up, right? Now, how do I scale that down? What is the most intuitive way to handle that? Any comments? Be it as simple as that. Yeah, Tarun, go ahead.
Do we use any weights like parameters to do that? Initialization of any parameters.
That's a good answer, but no. What we do is we just try to figure out the average of the entire thing, because yeah, normalize with number of words, that's the answer that I was looking forward to. So if you have sums, you have 500 words, you have 1000 words, you have 10,000 words, you can just average it out, and every communication still remains. It's very weak communication, I get that, but averaging it out or normalizing it is really something that I was looking forward to. Thanks for that answer. And what I'm trying to do here is a basic for loop in which I have this X bag of words, BOW, X BOW, which is just a zeros matrix of the same shape as X. So it's still BTC. And what I do with this for loop is that I iterate over each batch, I iterate over the time steps. And can you see this part? This is the entire magic. So I am trying to figure out the prefixes of the current word. So everything till t plus 1, everything till t plus 1. So once I move this indicator, I just want to take everything out of it. So the slice of the prefix. And what I'm trying to insert into the bag of words is the mean, torch.mean, of the entire previous prefix. And if I do that, what I get is a shape of 482, which is something which I want. So averaging is a good way of communication. And that's it, right? Thanks for the talk. Bye bye. Not so quick. What now? What I want to maybe give a guidance to the thought is that, does this make sense if you have a prefix of words and if you average all of the vectors? Does that hold enough information to maybe to forward propagate a generation? So if you average out all the students opened there, does that give me information as a model to predict books or maybe predict laptops? And that is where we come to the first hindrance. I don't want that, but I still want average. And this is kind of interesting, wherein I'll make this a little easier for you. I'm going to go to attention by holding on to this intuition of averaging everything, right? And with that, I'm going to create another cell and also go into a detour of efficiency. So, like I mentioned, sum is a problem, average, good. So it's normalized, the scales are good. Now, as a deep learning expert or a deep learning engineer, if I do this, as in if I do a for loop,
I,
if I do, yeah, go
there
ahead.
is a question like, is there any alternative rather than finding average?
There is, but I'm going to hold on to this question because I am going to cover this inside my talk. So just a little second, and I'm going to cover this. So what I'm trying to come to is maybe writing a for loop in the world of deep learning is a blasphemy. So how can I make this a little more efficient? And with this, I'm going to again take a detour and copy paste a bunch of code. I'm going to cover the code in here, right? So what I did is I have a b tensor, and forget about everything, just focus on efficiency of average. Forget about vectors, forget about words, forget about LLM bootcamp, don't forget about that. Forget about everything related to NLP right now. Just think about how to make averaging a little more efficient. And this is just a vector b, which has a range of 0 to 10. The shape of 3 2 is a float vector. And I also have a vector or a matrix A or a tensor A, which is just ones of shape 3 cross 3. And once I do this, what you'll be able to see is that I have A as all ones, which is 3 cross 3, B as a rand int tensor with the shape of 3 cross 2, that is 3 rows, 2 columns. And C is an interesting vector which holds A matrix multiplication with B. So, how many of you can already understand where I'm going to? 11 comes from the fact that I have to add 155. 23 comes from the fact that I have to add 968. So can you see that I'm already summing things up just by matrix multiplication and not by having to do it in for loops. So this is efficient, right? This is good. Now, another intuition about attention, or maybe how things work, are that if you have students opened their book as your corpus and you want your prefix is students and you want to predict opened, right? But you don't, and you also have their books inside of this corpus. Now the question to the audience is, do you want the model to know what comes after this opened, or do you just want the prefix? In a language model, do you want anything in the future to take care of this language modeling, or are you only interested in the prefix? And I'm going to take some time because I'm thirsty. I'm going to drink some water, and I'll come up with the answer. Maybe Tarun can help as well. So just to reiterate, the question was, if you have language modeling setup, do you need the future tokens to participate inside of this entire language modeling task, or or do you, or should you just take the prefixes into account? I'll wait for maybe 30 seconds, and anyone with an answer would be like really nice. And people who are watching this in the recordings later, please feel free to comment it inside of the comment section of YouTube, or maybe just pause this video and think about it for a minute. What is it that we really want here? Do we want future tokens? Do we want past tokens? Do we want both? Do we want only future tokens? What is it that we want? Right. For the sake of time, I'm going to say that with language modeling, we don't really use this future tokens. We just take care of the past tokens, that is the prefixes. And with masked language modeling, we take care of the future tokens and the prefixes as well. So what we are going to cover is only language modeling. So we don't want to, we need future tokens, but for classification it has prefix or the first word embeddings two words. Good answer. So that's something which I was looking forward to. Thank you for that answer. And now let's come to this another hiccup that has occurred inside of our code. So we first started with communication, how to communicate between the prefixes. A summation works, but an average is better. Now with for loops, we can average it out. It's pretty simple Python code. I'll just go up. This is like 8 lines of code works. To make it efficient, what we did is matrix multiplication. Just torch dot once, a at the rate, and at the rate is torch dot matmul. It's just a symbol that we use. A at the rate b gives you the same thing. And what I'm trying to come to is, we don't need the sum of all the things that comes in the future. What are we going to do? And this is where a nifty trick comes into play, wherein we use the lower triangular matrix to have the entire thing laid out to us. I'm just going to let it play. So what happens now is, this row gets dot producted with this column. Now can you see that 1 when multiplied with 1 gives you 1, but all the zeros multiplied with 5 and 5 does not let the future tokens have a say inside of the average or the sum. Till now we are just doing the sum of the output of the matrix multiplication. So if you have a lower triangular matrix, you are inherently using a matrix that can help you prohibit the future tokens from having a say inside of the current or the current representation. So that's really interesting. Now how do we do average again, Aritra? Sums are good, but you said it's not very feasible. Worry not. Here is another code snippet. And as you can see, if we just divide the A matrix or the lower triangular matrix with the sum of the individual values, we are essentially normalizing the A matrix. So once I let it rip, you can see that this A matrix has is normalized. That is what I'm coming to. So 100 is normalized, 0.5 normalized, 0.33 normalized. Now once you have this entire matrix gets multiplied with the matrix B, you are going to have an average. And please understand that this average also contains the only the prefixes, not the future tokens, due to the fact that it is a lower triangular matrix anyway. So what we covered communication. We need communication for good representation. Why do we need good representation? For the model to predict better. Now the communication can be in the form of summation, but summation is not that good. Hence we come to average or normalizing it. So we covered for loops. We also went from for loops into a detour and covered how we could do this, how we could replace for loops with efficient matrix multiplication. And this is like a little quote that me and Ritvik use a lot. We can boil down deep learning into matrix manipulations. And if you have been to any online talks or offline talks where we both are taking on, like we are on stage, you will find us throwing that quote quite often. So going forward, now let's get back to the basics. Now that we have understood how can we model this for loop into matrix multiplication, why not we do the entire thing with our word vectors and make use of matrix multiplication? And that is how we come to this bit wherein everything remains the same. I've just used fancier terms, but everything remains the same. See, for example, torch.trill, torch.ones, torch.trill, torch.ones. This is just the A matrix. The A matrix is now normalized. The same thing happens here. And the outputs or x bow 2 is just the weights at the rate of x. So weights are nothing but the weights that we want to derive, and these weights when multiplied with x give you the bag of words or the average of the entire thing. Now what torch.allClose does is checks whether xbow that is used in for loops and xbow2 that was built out of this entire matrix multiplication are same or not. Fingers crossed, and that comes to true. So essentially what we boiled down our entire for loop is in 3 lines of code wherein we build the weights or just a matrix. For now, don't think of it as weights of a neural network. Just think of it as a matrix that helps do average, but also in a restrictive manner, because the average does not take care of the future tokens, and that is something which we want in language modeling. So weights by torch.sum, and xbow is nothing but weights at the rate x. So this is how the entire for loop can be replaced with. Now going back to the collab notebook, I'll just create another code snippet. And this is a little interesting, and I'm going to take as much time as I need here, because this is the heart of the entire workspace that I'm trying to build. So this code essentially creates another bag of words, and essentially x bag of word 3 has to be same as x bag of words. And let me just try with it and see whether it's true or not. Yes. So you can say that there is no hard coded logic inside of it. So I don't know what x bag of words is. And I could not possibly make x bag of words 3 be equal to x bag of words in a handheld fashion. So the entire code base is just another way of looking at at everything. So I'll go in step by step. The first one is torch.1, torch.trill. So this is nothing but, if we go ahead and printed this should come out as a lower triangular matrix, right? So if you thought about it, it's T cross T, that is 8 cross 8. It's a lower triangular matrix with all zeros in the top, ones at the bottom. Weights is changing, so I can't print it out right now. So what weights does is it starts with zeros, and this is essential to understand because uh, in the later part of the stream I'm going to talk about weights a lot. So it starts out with zeros, and we use something called masked fill. So masked fill turns out that wherever the trill is equal to zero, that is all these parts, wherever these are zero, just put a negative infinity to it. And why negative infinity? I'll come to that. So don't rush into thinking why this is negative infinity. Just to recap, I have a lower triangular matrix. I have a separate matrix that is all zeros. I am filling out these all zeros in places where the trill or the lower triangular matrix is zero. So all of the zeros wherein the lower triangular matrix is zeros, I'm just putting them as negative infinity, and then I'm passing it to a softmax function. And what does a softmax function do? Softmax function does an exponential of like e to the power of minus x, 1 by e to the power of minus x, something like that. So if you go to softmax, this is what essentially the formula is to e to the power zi by the summation of the entire thing. This is a normalizing factor, and softmax is very frequently used, so think about it. And now let me ask you this question: what is e to the power of minus infinity? Anybody in the chat, or maybe Tarun? What is e to the power negative infinity? So 1 by e to the power of infinity would give me, anybody in the chat? I'm going to spend some time on this code snippet because this is going to be the heart of the entire workflow. Tarun, if any comments or if you want to answer it, feel free to. This is where I'm at, and this is the thing that I want to ask a question about. So if I do a softmax, and what is e to the power of negative infinity?
Is it 0?
Yes, it is. So what this entire thing does is that if you have weights which are right, Satish, if you have weights that are all zeros and you have certain positions wherein you insert negative infinity and the entire matrix goes into softmax, you're essentially going to get zeros at places where you have negative infinity, and you are going to also normalize the other spaces. This is ingenious, right? You need this function in a way that also normalizes but also takes care of this future tokens not perturbing the current representation. So you take zeros, you fill out the places with negative infinities where you don't need like the future tokens, and then you pass the entire matrix inside of softmax, and the softmax formulation is done in such a way that is e to the power negative infinity goes to 0. So every position where negative infinities were placed, it just turns them off. And also in the exact same row, all the places which have values or maybe they were not negative infinity, those are normalized. And this is essentially what we got here. So after softmax, the weights are going to look something like this, right? And this is something which blows my mind till date. And right after softmax, it becomes very simple what you're going to do. You're just going to take that average out weights and you're going to do a matmul with the weights. So that is going to give you what we first started out with. So communication, summations are bad, average, good, but we also don't want the future tokens to participate in the entire language modeling setup. So we kind of tell the model to or tell the matrix to not give weights to it, hence zero out those weights. And that was done in a for loop, that was done in matrix multiplication, and that is now done in 3 steps or maybe a little more, but it's done in a way that is very intuitive. You have a lower matrix, you have zeros, you mask the zeros with negative infinities, wherein You don't want those future tokens to take part. Put that inside of a softmax, you get good weights or normalized weights, and now you do a matrix multiplication with the inputs, and that gives you like the actual x bow that we had first begun with. Right. That is a lot. I'm going to stop for a while. Look out for questions. Maybe 30 seconds or so. If you have questions, type it out. I'm waiting. I'm also going to, yeah, Tarun, if you have any questions.
Uh, so this torch drill, it is mainly used to get the lower part of the matrices, right?
Right. Yeah, yeah, yeah. So due
Okay.
to the fact that it's all ones, torch.trill just masks everything in like the upper part of the matrix is all masked with zeros, but the lower part remains as is. So if it was anything in the spectrum of random, we wouldn't have been getting ones, and instead of ones we would have gotten random numbers. So torch.trill just essentially gives you a lower triangular matrix, the matrix that you feed. That's what it does.
Is it for the batch matrices or the complete one?
I'm sorry.
So mainly torch.trill it is also used to get the batch of the matrices, right?
Batch of the matrices, as in the you had B here, you're saying that you would also get a vector or a matrix with the batch dimensions inside of it, right?
Yeah, exactly. Yeah.
Yeah, yeah, yeah. It'll just give you lower matrices of the entire matrix that you're trying to get in. It's just going to turn all of the other values as zero. That's all it's going to do.
Okay, got it.
That was a good question, by the way. So moving on, what we have covered till now is kind of very hand wavy. We are 40 minutes inside of the live lesson. We haven't touched upon attention. And this is where I take another code snippet and talk about it a little more. This is going to be a little, I think it's visible. Right. So, what I did here is I'm going to start off with a single head attention mechanism, and then we are going to also talk about multi head. But think about the entire process that we covered. So, what we covered was a means of communication of the prefixes in a way that all these prefixes average out their representation into one single representation that goes into a model. The model kind of gives us good probabilities, and that is what our assurance is. Now, remember how I told that weights, when initialized with zeros, is something that we want here because we just want averages. Now, the question is, and this is some food for thought, and I'm going to answer this, and this is not a question for the live audience here. The question which should come up right now is, what if we did not initialize the weights with zeros? What if we initialize the weights with something other than zero? Does that mean that the averages are going to be a little different? And if you're thinking about it right after the code snippet was run, I am happy because I could guide you into a place which has a void, and that void was filled by attention. So if the weights are not initialized by zero, and if the weights are something that are initialized by little numbers, real numbers, any numbers, it essentially means that all the places uh, where the numbers are not zeros, it's going to give that amount of weight to that prefix. So students opened their book or something or the other needs to get an attention of students more and opened rather than there, right? To have a good probability of books or laptops, it needs to know who is opening what. It also needs to know, am I being opened? So maybe a laptop opens, a book opens, but also a pencil box opens, but something or not something which opens cannot be a good probability. So, does this intuitively mean that we need to attend to certain parts of the sentence more than the other parts of the sentence? And that is where weights comes in. If you think about it again, we need to have a weight which attends to these prefixes more than some other. So if we can't just have a random matrix and tell the model to, hey, start with this and learn it on your own. We could do that, but while we are talking about attention and if we want a solution to this, the last step of our transformer or training our transformer or just the attention mechanism should give us weights in which the prefixes get attended to certain parts, and also some representation gets lower attended, like low weights, for a good probability of the next word. So that is something which we build. And to build this, the intuition is each word has a projection now. Two projections mainly. One is key and one is query. So for students opened their books, let's say for example, books has this query Q. This is again just a very hand wavy way to explain this. I'm going to come to the code a little later, but all eyes on me. Now, what I want to mention is that each word has these two projections. So think about projection as just a fancy way of saying that I want to make two different vectors from this individual vector. So a word has a vector, and this vector is in a space. Now I just want to project this vector into another space, and I have another vector. And why do we need this splitting? I'll tell you like in great depths. But right now, just a vector, and you have a query vector. And you also have key vectors for each of these tokens. Now, a query vector is essentially, hey, I have a query, and does anybody know which key I need to match to? Right? So think about this analogy again. Books, the query of books needs to have a key of, like, a key would be good for students and key would be good for our opened, the term opened, rather than the key which is coming out of there. So every individual word has a query and key. The query gets the weights drawn from these keys. So think about query being a tag, which I'm looking forward to. And every key vector that you have in the prefixes kind of gets a similarity score done out of it, right? So query and key. And I also saw a glimpse of a question. I'm going to take that question right now. I don't know if you want to again flash that question.
Yeah. Is key, query, and value used for attention weights or context vector?
It is used for attention weights, and essentially the key and query are used for attention weights, and value, uh, once you have those attention weights and multiply that with value, you get the context vector. But that is too high level right now just to give out the answer. I just blurted out the answer. But what I'm trying to come to is the intuition of why you need a query and a key. So going back to what my analogy was, the entire average is not that great. If you have weights which start with zeros, you are putting in attention at each and every individual prefix, but that's not what we want. We want individual words to pop out for a specific probability. Like students opened there, students unopened should be weighted much higher than there for a probability of books and laptops. So I have this query. I'm trying to figure out which key of these prefixes are good, and how do I do that? The most beautiful and most simple way of doing that is doing a dot product of this query with all the keys, and the dot product is going to give me a similarity between the query and the key vectors of all the prefixes. uh, Dot product being high means that this word that has a high dot product needs to be attended more. So again, going back to the analogy, students opened there, and the book query vector needs to have a good dot product or a higher dot product to students and opened than a good dot product to there, right? And that is the analogy that we are trying to build. once we have these Once we have these dot products, we are essentially, what we have is weights, right? And this is where we are at. So if we have our weights initialized properly, we can then go on to our matrix multiplication again with the inputs, and we get a good representation. And I'm also going to take questions. Is If you initialize other than 0, then it won't be exponential. 0 is equals to 1 in the diagonal and lower diagonal part, which won't give you the average. Am I correct? So if you don't start with zeros, yes, and in softmax, that is not something which is going to happen, and you're absolutely correct. So you start with zeros just to essentially get a hang of the average part and not the future tokens. But now I have moved on from initialization of zeros to maybe understanding or building the intuition of what these weight vectors or weight matrices do. And the second question is, I think you're on mute.
Okay, so I guess we only have these two questions.
Okay, cool.
And one question is from my side, like
Yeah.
in the context of what Satish had asked. So
Mhm,
instead of zero, if we initialize random in this case, so will
mhm.
it affect in the performance, or it's just an experimentation?
See, for this block of code, what I'm trying to come to is just averaging, and averaging does not have to be perfect, because if you start with anything other than zeros, the softmax is not going to give you a normal distribution at each rows, which is in turn not going to give you an average. So I'm not training the module right now. Does that make sense? I am just coming to the idea of how we can go from sum to average, and then from average to maybe keys, queries, and values. Does that make sense?
Yeah, sure.
Cool. So coming to this part, what we did in a very hand wavy way, and I am also going to go scroll to this. Okay. So what we did in a hand wavy way is we have these words. Each word has this query and key. And for now, just don't look at this. I have this just because it's easier for me to have everything, every code inside of one cell. Just don't look at values. We just have queries and keys. And what this essentially does, that torch.nn.linear, is just a linear projection of whatever I have in X. So see, for example, K and Q are keys and queries of each of these individual words. And what we do here is essentially the entire thing laid out, but just that the weights are now a dot or a matrix multiplication of Q query and key. What this does is that it does not initialize with zeros. What it does instead is have a dot product, or whatever we were wanting, a dot product of the query with all the keys that are there in the prefix. And also, due to the fact that it's torch.trilled, that is a lower triangular matrix, it does not let the future tokens take part inside of this weights. So a little journey through the entire collab notebook is, you need to communicate your prefix. The communication can be done with summations. That's good. The communication can be done with averaging, because that is normal, a little more normalized. We can do that in for loops. That's good. We can also do that in matrix multiplication. That's better. We could also do that with softmaxes inside of it, because we need softmax. And why we need softmax when we can just do that in matrix multiplication? I think this is a question that has been popping up recurrently. But I'll go back to why we need a softmax in just maybe 5 to 10 minutes. So right now, where we are at is just averaging it out, but we also need to understand these weights. When they start with zeros, they attend to each and every word equally. We don't need that. We need specific words to pop out inside of this probability. We need the help of attention, or maybe we need to attend to certain parts of the prefix more than certain parts of the prefix for a good probability. So what we do is we just don't initialize with zeros. What we do is q at the rate k. That means a matrix multiplication of the query matrix with the key matrix. And why do we do that? Due to the fact that we want a similarity score or a similarity function. If you are into transformers research, you will find this similarity score, attention score, similarity functions coming in a lot. So this is just an attention score, and we mask all of that to minus negative infinity. That is, we don't want the future tokens to take part inside of it, and we pass that into a softmax. Now, essentially, what these three things are doing is that it builds the weights on which we want our entire attention mechanism to formulate. We want weights to be assigned to good words, as in the words that are needed in a probability. Now comes the value, wherein due to the fact that we have this word vector which has been linearly projected to query and key, why not we also have this another projection that is a value, and we use that value projection inside of our matrix multiplication. So think about the entire workflow again. We have x, that is the input. X gets projected to key and query. Key and queries are something that makes these weights. This is also masked due to the future tokens not taking in the responsibilities of perturbing the entire equation. We pass that into a softmax, and then we do an output. We basically build an output by using the values. And this is this might be a debatable topic, but what I have seen over the like in my experience is that the more we decouple things, the better models learn. So what do I mean by decoupling? So think about a word having a vector pointing here, right? If that word vector is the key, is the query, is the value itself, all of this is this vector, this is going to have very strict how do you say it, very strict transformations applied on it. It cannot work as a key, it cannot work as a query, it cannot work as a value all at the same time. So we are decoupling all of its actions into three different vectors. So hence we are projecting this word vector into three different categories, that is query, key, and value. And each of these categories has its own individual action to take, right? So the key vector can move in its own space, the query vector can move in its own space, and the value vector can move in its own space. Everything is decoupled, and the world is a better place to live in. That's essentially what this is. So now that you all kind of understand what this single head attention does, single head attention mechanism, I'm also going to talk about a little caveat, and then we'll move back to slides. So if your q and k are just random vectors with the essential batch size, time size, and head size, and you do a weight of q k dot transpose, that is essentially this, and you run this, a little problem. Head size is not defined. I'm sorry about that. Didn't run this. Okay. So if you run this and you try to figure out the variance of k, you will see that due to the fact that it's a random normal distribution, the variance should be around 1. That's good. If you also run a variance of query, it also should be around 1. That's good. But what happens if we do a variance of these weight matrices? This is not 1. And that's going to be a problem. If the distribution is so far spread out, the variance is so far spread out that it's not 1, it's essentially going to go into a softmax function, right? The weights are going to go into a softmax function. As you can see, these weights are going to go into a softmax function. And if you do a softmax of a tensor or a vector that has huge variances, it's going to peak out. And that's not good because of a bunch of reasons. The first reason that should come to your mind is bad gradient flow in the backpropagation algorithm. So if you have a peak value and everything goes down to 0, all of these 0 vectors or all of these places where there is 0, the backpropagation or the gradients don't flow, and that's bad. What we can do, and I'm just not going to wait till this, I'm also going to give you the solution. What we can do is qk transpose, and you just do a by root over head size, that is the dimensions that you have. So just do a root over head size, and you do a weights dot var, and if you let that run, you'll see that it's again scaled back to 1. And why do I do this? Why am I confusing you with a lot of jargons? I'm going to come to this very soon by presenting the slides. And this is where we are at. This is the same entire code that we covered, just with our friendly scale term. And everything should look familiar. And the discussion here that I'm trying to come to is the, can you see this part? And I'm going to take the laser out. This part is where the term self comes from. Why is the term called self attention? Self attention comes from the fact that key, query, and value all are coming from the same input. So it's essentially one input that builds out this query, key, and value, hence self. And also this part, that is weights, which are masked filled at the lower at the upper triangle, which are filled with negative infinity, that builds the causality. What do we mean by causality? It's just a jargon, don't fret. Causality means that we don't want, not causality, causal means that we don't want the future tokens to take part in the representation of the language model. So if we have negative infinities, those essentially go to softmaxes. Softmaxes have a formulation that essentially turn these negative infinities into zero, and hence that is good for a causal model. Now, a neural machine translation, and this is English to Bengali, has two parts, encoder and a decoder. Encoders have attention mechanisms that are self non-causal, while decoder has attention mechanisms of two kinds. One is cross causal and self causal, right? Both of them are causal, but one is self, one is cross. And we come back to back to these slides, and how do we make the self part cross and causal to non-causal? The self part can be termed as cross attention and not self attention only when the query comes from the decoder and key and value comes from the encoder. So going back, this is your X, right? This comes from the encoder. The encoder should give you the key and value, while the decoder should give you the query. And the query comes from a different part. Key and value comes from a different part. Hence, not self, cross. Cross between the two things that we have in mind. And non-causal, if we just remove this entire workflow, that is, we just don't mask fill with negative infinities at the upper triangular matrix, we can remove this masked fill, and essentially what happens is every token takes part in the representation learning. So we are saying that, hey, I want future tokens, I want past tokens, I want the current token as well. So give me a communication between all of these tokens, everything all at once. So just remove the masks, you will get the cross non-causal attention at your service. So that's something which I wanted to cover. With that, this is my last slide, and this is essentially what we were coming to. So let's go back, take a quick recap. We started with what language modeling is. We went from language modeling, we understood what probability of the current word is with prefixes. How do we communicate the representation of the prefixes to get a good language model working? We understood that was probable in for loops. We did matrix multiplication. We also did that in softmaxes. We had a bunch of heads and whatnot coming in. And we are at this point where we understand what query is, what key is, what value is, what attention is, how things work. Absolutely pristine. Now, what transformers did, or the paper attention is all you need did, is that this is an encoder, this is a decoder. And can you see that the first is a multi-head attention, and we covered single head attention, right? If you stack single head attention into like multiple times, you essentially get multi-head attention. And for the encoder, also this is a fair bit of warning, transformers were essentially built for neural machine translation. So essentially you have one language which comes in, so let's say English comes in, and it gets encoded into a representation. Everything gets encoded into one representation, and the decoder takes this encoder's representation. It also takes the start token or maybe something in Bengali to start off with, and it is an auto-regressive model. That is essentially the language modeling part that we are coming to. So you get this encoder representation, you also get inputs from the decoder, and it gives you the next word, next translated word in the language that you are trying to build the neural machine translation model on, right? So in the encoder, we need all the representations of the input. So say let's go here. Where are you going? This is the English sentence that gets into the encoder. And what I need essentially is a representation that is built out on the entire thing and not just the prefixes. We need the entire thing. So what we are going to take care, what we're going to use is causal. Are we going to use causal or non-causal? We are going to use non-causal, because we need the future tokens to take part inside of this representation building. We need all of it all at once. So that's good. Do we need cross attention here? Do we need something from the decoder? We don't. We just need everything that is coming into the encoder. So what we need is a non-causal. We also need self attention. So these are the two things that gets here inside of multi-head attention. And multi-head, due to the fact that it's not just single head, it's a stack of all these attention layers inside of one big layer, that is the multi-head. And you normalize it, you add residuals, you feed forward it, and you get a good representation. That's it. And with output embeddings, what we are essentially coming to is, if I give a start token and I enter a start token, I should expect my decoder to give apni, that is a word in Bengali, that should come as a translation, verbatim translation to what we are doing here. Where are you going? Should be apni kothay jaচ্ছেন in Bengali. So let's take it down again, step at a time with the decoder. So encoder gets in the entire thing, self attention check, non-causal check, everything gets in, the representations come out from the encoder. Now the first step inside of this decoder.
Hi,
Yeah, Tarun.
Aritra.
Yeah, yeah.
So there is one question like,
Mhm.
can you please explain the causal and non-causal intuition again?
Right. So causal and non-causal intuition is, once you have a language model, you just need a prefix, that is students opened there. This is the prefix to have the model predict the next word, right? In this kind of setup, you don't need anything else in the future. You cannot essentially have anything else in the future to take part in this probability. That completely beats the entire process of generative modeling or autoregressive modeling, wherein you just give the past tokens and you predict the future tokens. You don't have the future tokens already at hand. So that is where the causal part comes in. In the encoder, what we are trying to model is the entire input all at once. We need the future tokens, we need the past tokens, we need the current tokens, everything comes in. We are essentially trying to model the English language all at once, because we are not trying to figure out what comes after, say, where are you going. I'm not trying to figure out where are you going and the next word after that. I'm trying to model an encoder in such a way that the entire thing, as in the entire sentence, where are you going, has a good representation enough for my decoder, who is a language model or a generative language model, to take care of that predicting of the next words one after the other in Bengali. Does that make sense? So encoder does not need causal, as in encoder needs all the future tokens inside of it. So we are not prohibiting anything in the future. We want everything inside of it. Decoder, on the other hand, does not need future tokens. It just needs encoder representations and one token at a time, just to get the next probability. Does that answer the question? Cool. I think I'm ready for the next question, if you have one.
Until Satish replies back, there is another question. Like,
Mhm.
can you tell what happens in positional encoding?
I will come to this a little later, because that is something which is a caveat. Okay, Satish says yes. I'm happy. Positional encoding is something which I'm going to work on.
Okay.
Why not
So,
use masked multi-head attention in encoder? If you use masked multi-head attention in the encoder, you are essentially trying to model the encoder as a language model, which is something which we don't need. So think about it. If you have an English language which needs to go in let's just break it down. In Google Translate, what you are trying to do is you are not trying to autofill your English to get the translated language. If you would have done that, autofill your English as well as translate the language, masked multi-head attention in encoder works. Does that make sense? The intuition is here to have all of the input all at once, have a representation that is good enough for the encoder to model properly, and in the decoder have a autofill kind of autofill workflow. So you have the entire encoder digest every input word, not use masking and whatnot, but the decoder needs to spit one word at a time. So that is where you don't want the decoder to see the future tokens. It's kind of building that intuition inside of it. Does that help? I'll maybe I'll continue. Tarun, is that good? Maybe I'll continue and wait for an answer again.
Yeah, we can continue.
Cool.
If anything pops up, I'll just add it in this screen.
Okay, good, good. That would do. So neural machine translation, encoder, decoder, masking, not masking, everything goes off the bat. Another little, that's great. Another little caveat here is, can you see the color scheme? So all these color schemes are tell you that, or not color schemes. Let's just go with multi-head attention and masked multi-head attention. Multi-head attentions here are the points where we need all the tokens coming in, and masked multi-head attention here tells me that there needs to be a prohibition in the future tokens. I don't need anything from the future. I just need everything in the past or the prefixes, and everything kind of flows from there. So that is something which we kind of notice in the diagram itself. In the encoder, we just have one attention layer. In the decoder, we have two. One of them is a cross attention because I need to know what I am translating. That is the basic intuition. I need to know what the English language was in order for me to translate it into Bengali. That is where the cross attention comes in. The key and value comes from the encoder, and the query comes from the decoder. So that is essentially it. Feed forward, normal layer, softmax, these are some things that you know. Now, coming to the question, what and why do we need positional encoding? Let's go back to the code. And this is kind of interesting to think about. If you have a prefix of words, say students opened there, and you do an average, maybe weighted average, do it, everything that is pointed out here. The upper triangular, the weights, which are nothing but the query times key, the similarities and all that. What happens if I just reorder the words in the prefix? So my first order was students opened there, and my next order is there opened students. The other order is opened there students and whatnot. So think about it. Is it going to be the weights are going to be giving me the same value, or the weights are going to change? And this is something to ponder upon, and I'm also going to leave it to the audience for an answer, because this is something which is really important, and also basis on why we need positional encoding. So if we just remove the order or maybe reorder the words, does that help? Or is there a way the model knows that the order has been changed? Are we going to get the same weights, or are we going to get different weights? And Tarun, you can come up on screen, because anyway, we are going to close in maybe 5 minutes. If you have any comments, post them out, or maybe you yourself tell the answer.
Regarding the positional encoding, right?
No, so the question was, if you have a prefix of students opened there, and you want to model the language, as in you want to have a probability of books or laptops. And what we are essentially doing is doing a sum, average, weighted average, and whatnot with these prefixes to communicate. Now, what happens if the weights in these weights, if we just reorder the prefixes, like students opened there, I just reordered it to their opened students, or their students opened, or just reordered the words, is this going to give a different weight, or is it going to give the same weight? That's the essential question.
It's gonna give the same weights, right?
Right, exactly. So that is a problem. If you have English, or maybe any language, code, English, French, or anything other than that, in this current implementation, the weights will be reshuffled as you reshuffle the tokens. That's incorrect, because weights are not going to be the weights are essentially just a matrix of q at the rate k, and these are filled with maybe future tokens. If you I'm talking about the prefixes, so that if you reorder the prefixes, the weights are going to essentially remain the same. There is no way that the model can understand that the prefixes have been changed. And what is the problem here? If you can see right through the problem, is that language is made out of rules. You need certain words or certain tokens to be in front of certain tokens. You need certain tokens to be after certain tokens. So this order is really important. If you reshuffle them and they essentially give you the same outputs, that means the model does not have permutation invariance or permutation variance. Permutation variance. So it does not know how the permutation is going to affect the model, and that is bad. And that is where, if I go back to the slides, that is where positional encoding comes into play. So what essentially positional encoding does is it gives you a vector representation of positions. So say for example you have positions 1, 2, 3, 4, 5, and these numbers are represented in certain ways, in maybe just a linear projection of 1 to a vector. And essentially what we do is we add these positional encodings into our inputs. What that does is, now if you reorder your words, the positions are all the tag of the position or the position encoding also gets reshuffled, and that is essentially going to reorder my entire weight matrix. The weight matrix is not going to give you the same output regardless of what you did, like what, whether you have shuffled or reshuffled or not. And that is something which we want. So essentially what we say in deep learning, in deep learning space, is that as attention, self attention, cross attention, whatever, attention is permutation invariant. That is, it does not know whether the orders have been reshuffled. What we do to combat that is add positions and information of position, and that is essentially done by positional encoding. I think that kind of makes sense. Whether that has answered or not, I'm going to look out
Okay,
for
so
that.
I have a question.
Yeah.
Like
Mhm.
in some of the article I read related to the positional encoding, there was a theory that if you have a context, now let's say I have the context of the length size of 5. So now this
Mhm.
token size is of odd, and now I have one more context. Now this is of the even positioning. So do we have any mechanism to tackle both these different contexts? One has the length of odd, and one has the length of even.
If
So
you think, yeah, go ahead. Sorry.
yeah, so in positional encoding, the formula is something related to cos and
Right.
sine. So how does this context is tackled in positional encoding?
Okay, so right in the paper, what they have studied is a frequency of natural numbers. So 1 to 100, you do a sine, cos, whatnot. I'm not going to go into greater depths of that, because we can dumb it down. For a lack of a better analogy, we can dumb it down to just numbers and projecting numbers into context vectors. So if you have maybe 5, 6, it does not matter, because every position is unique, and every unique position gets a unique vector. So if you have a variable length with odd size, if you have a variable length with even size, it does not matter, because every number is essentially unique. So that is somehow why positional encoding works off the bat. And there are numerous keras.io examples that I have written, Shaq Paul has written, Akash Kumar and Ritik Raha, everybody. We kind of dumb it down to not cosine and sines. We dumb it down to embeddings of numbers, of like tf dot range works, and you just have an embedding of these unique values, and that works. So don't have to think about anything else. And these are all learnable parameters, so you can also learn the positional embeddings, which makes it really interesting.
Yeah, thanks.
Cool. So with that, I'm going to close out. And just before doing that, the references that I have used. One is let's build GPT from scratch in code spelled out. This is a wonderful YouTube session done by Andre Karpathy. And the entire collab notebook that I had shown has been verbatim taken from his collab notebook. So if you have already seen that, it's going to look as if I have like just copied and pasted everything. I just liked the intuition so much that I just wanted to have everything from his collab notebook and kind of use that intuition of building one on top of the other. The other is a course on advanced natural language processing that I have been following for natural language processing and transformers. So that's good from UMass. And a deep dive into transformers with TensorFlow and Keras, part one from PyMet Search, that is where I work, is also my take, my and Ritvik's take on transformers, how the evolution of transformers came into play, how we can implement a transformers maybe in 500 to 600 lines of code, and it's all good to go. So please, and I'll also be sharing out the slides right after, and I see Ritik coming in. So I'll share out the slides right after the stream. So do follow me on Twitter. I'm going to post my slides there. And what I am trying to come at is read as much as you can on transformers because it's very intuitive how this came into play. And best way to read is PyMet search. Best way to watch or ingest content like that is Andre's course or maybe Umas's course on advanced natural language processing. And with that, I'll take some questions if that permits. And that's about it from my end.
Okay. So we'll wait for a few seconds or few minutes until we have few questions.
Cool.
And
Sure.
can you share the code link? I
Oh, I'll
guess
do
it
that.
was
Yeah.
answered.
I'll do that. So I do you want me to chat out the Twitter handle? That's my Twitter. I'm going to send the code as well as the slides right after the stream. So do keep an eye on it. Anything else? Yeah, that's my Twitter handle. So if you go to twitter.com/ this Twitter handle, you'll find me.
Now you can even do x.com and
Oh, yeah. You can do that too. I just like twitter.com, man. Just my bias.
uh, any questions regarding the transformers or cross attention, multi head, or anything related to whatever Aritra shared in 1 hour 20 minutes live session. If not, you can reach out to his Twitter handle and ask the questions related to transformers or anything related to deep learning.
Hmm.
Okay,
Sure.
I guess we'll end the session. Thank you, Aritra, to accepting the invitation and speaking about transformers and the approach which you took, starting with these. Okay. Uh, I was telling the same thing, like starting with the code from scratch and then moving on with the slides. It was a good approach, and if people are following from beginning, it's a good intuitive to follow. And yeah, I look forward for more session. And if
Absolutely.
you have
It's
any
been an honor.
questions, please feel free to ask. If not, we'll end this session.
It's been an honor for me to be speaking on transformers. Thank you, Satish.
Uh, okay. Thank you again. I guess we'll continue with the LLM Bootcamp live session on weekends again. And this week we will have how you can get started with working with open source LLMs. And on Sunday, you will be having live session on fine tuning LLMs by Abhishek Mishra, who is a tech lead and AI consultant at Intel at Firm Group. So he'll explain via code on how you can fine tune Llama to 7B model. I look forward for upcoming session of Aritra and Ritvik. And yeah, we have 7 more modules or 7 more live session to complete in this ongoing LLM bootcamp. And I hope it's gonna be fun. And we have frameworks like LangChain and Llama Index live session, which is coming very soon. And I hope during that time, many people will be like, okay, this is very easy to use. And now many people will be like, okay, there is so much of max, and we need to learn torch, pytorch or tensorflow. There might be more questions until we are till module 8. Once module 8 is completed, only thing what you'll be using is a framework. So yeah, that's one update from our side. And we'll also share the feedback forms on since we are halfway through the LLM bootcamp, we'll share a feedback forms, so that if you have any queries like or difficulties what you're facing, you can add those comments and we'll get back to you very soon. Yeah, that were my closing thoughts. And do you have any closing thoughts?
No, it's just great that we like it's a good approach of LLMs, and a bootcamp is always quite nice if it's intuitive. So thank you for joining in. I really hope that I could make at least one or two people understand transformers without being too math heavy, or maybe introducing the transformer paper and then going into it. I did a top down approach, so I think that's helpful. I'll also look out for DMs in Twitter if there is any part that has not been covered thoroughly. So looking forward to that. And with that, bye bye. See you next time.
Yeah, thanks, bye. See you soon.